Hi guys, welcome back to our ongoing discussion about protein folding and protein stability. Let's turn back to that example I left you with at the end of the last lecture, which was a demonstration of what happens when you take a well-folded, well-behaved globular protein and subject it to increases in temperature. For most proteins, like I said, that are well folded and what we would call well behaved, they're going to do something very characteristic. So here's that plot again. Here's temperature. And over here on the y-axis, we're going to put basically, fraction, let's say unfolded. All right, so it'll be 0 unfolded down here at the bottom, 100% unfolded up here at the top, which means down here at the start of our experiment, we have the fully folded protein at some nominal temperature. And as we raise the temperature, what's going to happen, right? We know, well, at first, depending upon how stable the protein is, not much is going to happen. Things are going to basically stay okay. And then at some point, the sample does that, right? And there is this, let me redraw that. That's a little, so there. So at some point, you reach a temperature where there's a sudden change in the fraction of the protein that's unfolded, and it very rapidly, very steeply goes all the way to 100%. And the protein up here, of course, is now completely unfolded, right? Okay, so there are a couple of things about this plot, about this phenomenon, because this is characteristic, like I said, of most well-folded globular proteins, well-behaved globular proteins, in particular ones that would be referred to as two-state folding proteins, which is a large number of the well-behaved globular proteins, by no means all. And there's some really characteristic things about this plot that are really interesting. One is, let's say we did the experiment going this way, right? And the curve tracks in this direction. Well, if we got up to the top, we've got 100% of the protein is unfolded. And now let's just cool it back down. What happens? Well, for a well-folded two-state folding, well-behaved protein, what happens is that the curve goes right back down the way we came, follows exactly the same curve from the unfolded state as a function of temperature, right back down here to the folded state. There's no hysteresis in the sort of thermal unfolding plots like this for a well-behaved two-state folding protein. That's one thing, right? That's pretty remarkable, right? So there's one, no hysteresis, right? Or another way to put this is it's fully reversible. Right? Another remarkable thing is the nonlinearity of that curve, how nonlinear that curve is, that sharp sigmoidal transition is characteristic of these thermal unfolding or thermal melting curves of well-folded globular proteins. The third thing that is really striking is if you went in here, say, in a little Maxwell's demon, and you were to peer in at various points along this curve, right? And you looked at the state distribution of the protein, what you'd find at any one of those points is only two things. You'd only ever find the native protein and the unfolded protein. Nothing intermediate. The protein at every point along this curve is either fully native or fully unfolded, right? In equilibrium with each other. So what that means is that at every point along this curve, these intermediate points, say, right in here at that 50% point, You don't have the population half unfolded, right? Half structured. What you have is half the population is native, fully folded, completely normal, and half is completely unfolded, right? There's never, for a protein like this, for a two-state folding protein like this, there isn't anything in between. There are no partially folded states. It's either all or nothing. It's binary. It's there or it's not, right? Okay. So these are all diagnostic characteristics of a folding behavior that I've highlighted up here at the top, which is that folding of well-behaved two-state globular proteins is cooperative, right? This is diagnostic of cooperative folding behavior, right? Oops, wrong tool. Okay. All right, so what does that mean, right? Okay, that's what happens. That's what we see. That's what turns out to be true. But why? Why is that the case, right? And I left that as the last time sort of an answer to this conundrum of the relative importance of the hydrophobic effect versus other interactions. So what cooperativity in a like definitional sense, right? What cooperativity means, right, is that, or at least I guess in simple terms, that any set of interactions that define a process whatever those interactions happen to be, right? They're not independent of each other, or I should say more formally, they're not energetically. Right? They're not energetically independent of one another, right? Okay. Another way to put that, a more formal way that will sometimes be rendered, is by saying that in cooperative processes that are cooperative, the interactions that define that process are also known as being thermodynamically linked. They're thermodynamically linked to each other, right? So when you think about folding, what does that mean? To have the interactions that define the native state be thermodynamically linked to each other. Well, you think back to our initial conundrum, an unfolded polypeptide, all that configurational entropy that the thing has to shed in order to get down to that unique or semi-unique native state. That makes any highly specific interaction incredibly energetically unfavorable, right? Because that means you've got to tie some things down geometrically in a very specific orientation. That's entropically super expensive, thus the large entropic barrier to folding. But once you can do that, if you can figure out a way to do that, once you get that first interaction made, the next one that's connected, that's linked by, maybe that's nearby, that's a little bit easier to make. And once you got that one, the next one's even easier. And then the next one, even easier still. And so what you can sort of begin to see then is once you get those interactions going, if they're linked to each other, they're dependent on each other. Once you get enough of them together, subsequent interactions get easier and easier and easier and easier. And you get this sort of rolling cascade, right? That's a sort of this nonlinear development or sort of falling off a cliff, sort of binary behavior that allows the protein to sort of fold and behave like a unit, right? As a single, even though there are thousands, millions, billions of individual interactions, they're connected to each other in such a way that the thing behaves like a single cooperative unit, right? And this also works in the unfolding direction, which is why this curve is reversible and things are in thermodynamic equilibrium all across. So you imagine a folded protein. Breaking that first set of interactions that are all non-linearly coupled up together, that's hard. Right? But once you pop that interaction, right, things start to jiggle around. Popping this next interaction is a little bit easier, and then the next one, the next one. So if you can break the first few, it's harder to do, but once you do it, the thing begins to unzip, right? And it blows apart, right? All at one time. Okay. So this has some really important, in addition to being sort of a diagnostic property of well-folded globular proteins, this has some interesting implications for thinking about the relative importance of what maintains a stable protein structure. So this brings us back to thinking about the sort of what makes a protein fold, right? Or maybe why does a protein fold? Well, we know it's because of the energetics, right? We sort of covered that, right? Okay, but now the question is, how is what we're coming to now. How does a protein fold? And that's really sort of, in some ways, the topic for discussion today, right? So this is, you know, sort of interesting sort of topic. If you imagine that unfolded polypeptide with all of its, degrees of conformational freedom that keep that protein, or the entropy, the conformational entropy wants to keep that protein as disordered as it possibly could. And you got to make that first set of interactions in order to get this folding cascade going. How do you do that? How do you begin to pay that price, right? If it's so expensive, how do you ever even get started? Okay, well, this has been a topic of active investigation in protein folding and protein biology for decades. And over the last, I'd say 30 to 40 years, part of the picture, at least, a reason why the picture is sort of coming into focus. And what's really come to be clear is the very first things that happen, that price is getting paid at the earliest stages of folding in two ways. The first is, of course, hydrophobic collapse, right? So that is, of course, directly related to that phenomenon we've been talking about, the hydrophobic effect, right? We'll come back to that in just a second. The other thing that happens, right, is local structure formation. All right, so think beta turns, alpha helices, right? These are the two things that happen at the earliest possible stages of folding, right? There have been competing arguments about which happens first, as one or the other, and I think it's probably coming clear that it's sort of a continuum for a variety of different proteins along an axis between these two effects. There are some proteins for which hydrophobic collapse is the most important thing that happens. For others, local structure probably happens first. And a large fraction, maybe the majority of proteins, are somewhere here in the middle where hydrophobic collapse and local structure formation all kind of happen at the same time. This is sometimes referred to the model known as nucleation condensation. We'll come back to that later. Okay, but what this sort of brings up now is the argument about, well, hydrophobic interaction, the clustering of that hydrophobic stuff in the core of the protein, that's so important. And people thought for a long time that this was the main thing that kept protein stable, right? And the rest of this stuff, yeah, it's kind of important there, but man, first order, maybe even second order, hydrophobic, the hydrophobic effect, the hydrophobic collapse was the most important thing in the world for keeping protein structure stable, right? So you think about that. We talked about this a little bit. What does that hydrophobic collapse mean, right? What's going on? Well, you remember from our previous discussion that unfolded polypeptide chain is going to expose its hydrophobic core, right? Those hydrophobic amino acids exposed into this polar solvent of water are not going to interact very favorably with each other, right? That is going to require the water to form these clathrate-like structures around the surface, that exposed hydrophobic surface, at physiologic temperatures, like 25 degrees, 30 degrees, 37 degrees. That's fantastically energetically unfavorable, right? Because it's preventing the water from interacting with itself in bulk, so you're losing enthalpic interactions there. you're losing the enthalpic interactions, the hydrophobic stuff with itself, and you're forcing the water to form, yes, these enthalpically favorable hydrogen bonding networks, these sort of ordered water networks, but that's entropically extremely expensive. So the system, this protein water system, in an attempt to minimize that free energy penalty, is going to do what sticking oil in water is going to do. It's going to try and force those hydrophobics together. They're going to clump together to regain the enthalpy, the London dispersion, van der Waals interactions between those hydrophobics, releasing that ordered water with this great, this wonderful increase in water entropy. And that's going to drive this hydrophobic collapse, right? Okay, so we know that's going to happen. We know that's super important, and data from 4 decades at least or more of work on protein folding has indicated, hey, yeah, it happens. It's super important. It's a big contributor. However, more recent work, I guess the last 20 or so years, maybe a little more, reevaluated or reassessed this old idea that hydrophobic collapse was the most important thing in stabilizing protein structure. But the problem becomes, well, what do you have left, right? I mean, you have hydrophobic collapse, right? And the van der Waals interactions that are sort of part of clustering the hydrophobics, that set of weak interactions are subsumed in the hydrophobic collapse. What do you have left to stabilize protein structure, right? All you really have left after those hydrophobic interactions are the weak interactions, other weak interactions we talked about. Right? Those are dipolar interactions, salt bridges, right, which are present, but they're certainly not in every protein. And biggie, hydrogen bonds, right? And remember what it is that holds a lot of that local structure together: alpha helices, beta sheets, right? That's all held together by hydrogen bonds, right? Okay, well, here's the problem. Those structures are held together by an interaction, a hydrogen bond, that those same interacting groups, those amide, backbone amides and carbonyls, can just as happily make with water, right? From a sort of microscopic point of view, those interacting groups, a hydrogen bond with water, right? The hydrogen bond's a hydrogen bond's a hydrogen bond, right? Makes it with water, make it with a carbonyl carbon, carbonyl oxygen. That amide, actually, who cares, right? Oxygen is an oxygen. We're just making it's isoenergetic, right? And that was one of the arguments that was made for a long time about why. So this local structure, so this, okay, it's a rounding error, right? It can't be that important because there's all this bulk water. Well, that argument misses one really important point, which is that the interaction, these hydrogen bonding and these salt dipolar interactions and salt bridges interactions, which are also weakened in the presence of water, are not happening on their own, the isolated groups, right? The problem that this argument misses is that the groups interacting in a polypeptide are not interacting in isolation, right? That a protein is a polymer. The amino acids are connected to each other covalently. And to understand why that matters, right, consider the following sort of simple toy model. I'm going to write out a relatively simple sort of example of protein that's going to fold, but it's only got 4 amino acids. It's got 4 groups that are going to interact. Okay, it's silly, but it gets the point across. All right, so here's my toy protein. I got site A, it's connected covalently to site B, it's connected to site C, which is connected to site D, right? And this protein, of course, can fold into an ordered structure. That's sort of this looped thing, we're going to say, that looks kind of like this, right? And whoops, I erased my loop. Okay, and site B here makes a specific interaction. Let's just call it a hydrogen bond with site C, and site A does the same thing over here with site D, right? And that holds our folded structure together. Okay. And we can write this a slightly different. We can imagine it all happens at one time, or we could say, well, what if this, maybe, it's not illogical to imagine that maybe we're going to do something like this first. We're going to go down here. We're going to make whoops. Let's make that BC interaction first, right? And then A and D are hanging in the breeze here, right? And then maybe we make that AD hydrogen bond, the whole thing comes together, right? So we can write down some equilibrium constants here, because the way we've been discussing, we know how to do that. So we can write down one, we're going to call this one K total, K sub TOT. I'm going to call this one K BC, right, for just the BC interaction. I'll call this one KAD, but in this case, the KAD that I'm writing down over here, this one, right, that's the interaction for the AD with assuming BC have already been made, right, the way I've written the scheme. It's not just the AD on their own, right? Okay, just keep that in mind. Okay, so that's one thing, but we can think about this in another way. We can think about those interactions in another way. What if we thought about B and C interacting just like the isolated amino acids, or a little piece of polypeptide, maybe, with C, right? And then D could even just be the isolated amino acids, right? And let's say these guys get together and they form exactly the same sort of hydrogen bond, right? But they're just the isolated amino acids, right? But they're capable, of course, of forming the same exact hydrogen bond. And we can say the same thing about A and D. Let's say A, oh, I screwed that up. That was supposed to be a B. At least I found that one. A and D, right? So A and D form their same hydrogen bond again, but these are the isolated amino acids. Well, we could write down equilibria for these guys too. Let's call these K1 and K2. So here's my question. Is KBC, remember, KBC is the equilibrium constant for formation of that hydrogen bond between the B and C amino acids in the context of the whole polypeptide. Is KBC or K1, is KBC greater or lesser than K1, right? Which one is bigger, right? And therefore, which one is stronger? Is it the K1 or is it KBC? Now you might want to pause the lecture here for a moment and think about that. Really think about it. See what you think. See if you can come up with a logic on your own before I give you the answer. The answer, turns out, is that KBC, the equilibrium constant for that interaction of the two amino acids in the context of this polymer, is a lot greater, is much, much bigger than K1, right? Now that's the answer. Can you explain why? The reason is that KBC is so much greater than K1 is a direct consequence of the fact that the sites are covalently linked to each other. Right? So another way to think about this is the synthesis, the reason KBC, the equilibrium constant for formation of that hydrogen bond in the polymer, is so much larger than the same hydrogen bond in isolation, is the entropic cost of orienting those two amino acids with all the other stuff they want to do. That entropic cost of orienting them so you could form that hydrogen bond, getting those molecular orbitals, those atomic orbitals to overlap with each other so you could form that dipolar interaction and get those guys close enough to share the hydrogen bond between the donor and acceptor, right? Remember, that's a strong orientational requirement. The entropic cost of doing that for isolated groups is super high, right? Because you got to lock out all those degrees of freedom. In the case of the polymer, a significant amount of that entropic cost, all right, of getting the guys close together to form that hydrogen bond has been paid when the polymer was formed, right? Synthesis of the polymer paid a significant chunk, not all, but a significant chunk of the entropic cost of having to get those guys close to each other, right? Okay, now that has some significant consequences, because what that lets us do in the context of this model, right, between KBC and K1, or KAD and K2, is we can define something, right? So one way to think about this is the reason this interaction is so stronger in the polymer is because the concentration, the local concentration of B and C, because they're stuck together in a polymer, they can't get away from each other, their local concentration is much, much higher than you could ever get that concentration free in solution, right? Okay, so what that means we can do is something like this. We can say, well, if that's true, we can kind of normalize that KBC equilibrium constant, however strong it happens to be, to the sort of reference strength for that interaction in free solution at the same absolute concentration of those two groups, right? The total concentration is the same. And that difference, that enhancement, that fold greater equilibrium constant, we're going to define that as a, I'm going to call it B/C effective, right? We're going to call that essentially, we're calling this basically an effective concentration. Right? Okay. And we can rewrite that, because that's true, the following is true, that I can define KBC as just being equal to whatever the sort of normalized free energy equilibrium associated with forming that hydrogen bond, the isolated groups, times the effective concentration of those two sites in that protein, right? And I can do the same thing with that other interaction, the KAD, right? K2. We're going to define an AD effective concentration, which also means that KAD is simply equal to just K2 times the AD effective concentration, right? Okay, that's cool, fine. So what does that mean? Well, what it means is that if we go back to this overall scheme, it means we can define this equilibrium, this total equilibrium constant, right, here, and we can write down an expression that folds these other terms into it, right? And an interesting result drops out of that. So let's go back down here. We can say, well, all right, that means I can write down an expression for K total, right? The equilibrium constant, which is just equal to the concentration of the product. And I'm going to represent the fully folded species with all of those hydrogen bonds in place is just A.B.C.D, right? So that's basically this species here. And I'm going to divide that, of course, by the reactants, right? And I'm just going to do that with a squiggle. All right, so my squiggle is this guy, the unfolded polypeptide, no interactions, right, over here. Okay, all right. I can also now write down similar expressions for the formation of those interactions, the individual interactions in the context of the full protein. So KBC would just be the concentration of the protein that's formed the BC interaction only, divided by squiggle. If you look here, right, I'm just now writing down that equilibrium. Now I can do the same thing over here for the KAD equilibrium constant. KAD is simply equal to concentration of the fully folded species, A, B, C, D, divided by the concentration of the protein that had just formed just the BC only interaction, right? So I'm doing this equilibrium here, right? Okay. All right. So with those guys, right, I can do a little rearranging, right? It's one of the things that's useful thing to do when you're thinking about problems like this. So I can solve this guy for the concentration of the protein that just has the BC interaction, and that's going to be equal to the KBC equilibrium constant times squiggle, right? And I can do the same thing here for the KAD, and I can solve this one for the ABCD, the fully folded concentration. You'll see why I'm doing this in a minute. This one would be the A times B times C times D concentration. It's just going to be equal to KAD times the concentration of BC, right? Times the concentration of the protein that just has the BC interaction. Okay, now the reason that's cool is now I can go substitution happy, which is how this sort of thing sort of works. I can take this here and I can substitute it in here, right? That's kind of useful because when I do that, I get an expression that looks like this. I substitute that definition there. My K total now is simply going to be equal to KAD times the concentration of the protein with just the BC interaction divided by squiggle, the unfolded protein concentration. Okay, but I've also got a definition here for BC, right? Look at there. I can take this and I can substitute in here. If I do that, what happens, of course, is that this equilibrium, the K total equilibrium constant, now is just equal to KAD times KBC times the concentration of squiggle divided by the concentration of squiggle. That's kind of cool, right? Because I can now cancel the squiggles, right? I cancel the squiggles out, and what I get is that the overall equilibrium constant for folding of that my little toy protein is just equal, of course, to the equilibrium constant for forming the AD interaction in the context of the polymer times the equilibrium constant for forming the BC interaction in the context of the polymer, right? That's kind of cool because now if I go back up here to my definitions here for the effective concentration of these interactions, here, whoops, I highlighted the wrong thing. Sorry about that. Here, these definitions here, right? I can substitute those into this expression, and what it means is that the overall equilibrium constant for folding of the protein is just equal to the amount of free energy available, essentially, in forming that hydrogen bond interaction, whatever it is, in sort of a pure isolated kind of sense, multiplied by the effective concentration of the BC interaction, right? Times, same thing for the second hydrogen bond, right? Or interaction, whatever it is, times the AD effective concentration. So those effective concentrations, another way to think about them is these are essentially like entropic correction factors. For the local availability of those interactions and their in the course of their ability to make that hydrogen bond or that other interaction, right? So what you can see, if you go back up to this sort of model here, because they're near each other, their ability to form that interaction is much less entropically expensive. And once one is formed, the next one, they're going to be closer together, right? So the AD interaction, once BC is formed, they're closer together, and there's a lower entropic penalty to pairing them up than there would have been forming those guys to begin with, right? And so on and so on and so on. So each of these interactions cascades into the next interaction, increasing the local concentration of other nearby groups, making them much, much, much more energetically favorable than the isolated interactions would be of the same sort of absolute concentration of stuff out in free solution, right? Now, these effective concentrations can, in principle, there's some arguments about exactly how high these numbers can get, but there can be at least an order, 2 orders of magnitude, maybe 3 orders of magnitude greater than the absolute concentration of water at 55 molar. Now, if that's the case, you can now see how a hydrogen bond, right, in the context of a covalent polymer can be massively more energetically favorable than the same group hydrogen bonding with water, because the local concentration of those 2 groups is order of magnitude, 2 orders of magnitude, maybe more, greater than the concentration of water. And that interaction is going to happen preferentially, right? At the 99%, maybe higher level. In fact, it may be even more dramatic than that, because you can take proteins and you can put them in solutions of stuff that destabilize them. Here's a good one, right? You guys know what this molecule is? It's a byproduct of almost all cellular metabolism. It's called urea, of course. It's also an extremely effective protein denaturant. Also known as a chaotrope, right? There's another one, another common one. You've probably seen this one before. This one's even stronger than urea, right? Let's see if I can write that a little more clearly. Come on, come on. Anybody recognize that one? It's ionic, right? Normally it would be paired out here. What you normally find is a salt with chloride ion. This is so-called guanidinium hydrochloride or guanidinium chloride. That's the same group that's on the end of arginine, but in isolation and at high concentrations. So urea anywhere between 6 to 8 molar and guanidinium anywhere from 4 to 6 molar. You put that in an aqueous solution, it blows up protein structure for multiple different reasons, which I don't ever really have time to go into, but it will blow protein structure up, right? You end up with a polypeptide that in terms of its sort of radius of gyration and average behavior looks like a random coil. It's unfolded. There's like no organized secondary structure. There's no tertiary structure. Protein's completely blown up. You put them in 8 molar urea guanidinium. Well, as techniques got more and more and more powerful, in recent years, last 10 or 15 years or so, what people have been able to do is to go in and look in detail at what's going on for a protein that's been put into these solutions. And the amazing thing is that in many cases, protein is not completely random coil. It's not just a completely stretched out piece of polypeptide. There's no hydrophobic collapse, there's no organized structure, but what people can see are flickering bits, even in 8 molar urea or 6 molar guanidinium, flickering bits of alpha helix and beta turn, and even little pieces of anti-parallel beta sheet, little bits of it, right? All these local interactions flickering in and out of existence, even in this massively destabilizing denaturant, right? And what that means is those local interactions, even in the face of a destabilizing solution condition like guanidinium or like urea, those local interactions are so strong they can transiently overcome that destabilizing free energy, and they're already there, primed up, trying to interact with each other. Okay, all right, so we'll stop there and then we'll consider some of these ramifications in the next section.